I want to work through the practice test or test one. I'll work through the true-false questions, the conceptual questions, and then I'll go on and work through the fully worked out problems, the numerical problems. So the first question, question number one, asks us to consider arrangement of two charges, Q1, Q2, and the pattern of electrical field lines surrounding those charges. And from that pattern of electrical field lines, we've got to respond to four statements here. So the first statement says that the two charges have the same sign. So by looking at a pattern of field lines and looking at the pattern of field lines around charges, you can tell the sign of the charges. Field lines come out of, radially outwards from a positive charge. Field lines go radially inwards into a negative charge. In this particular picture, the field lines are coming out of Q1, they're going into Q2. So in this picture, Q1 is a positive charge, Q2 is a negative charge. And so the two charges are not the same sign. This statement is false. Second statement says that charge Q1 is a positive charge. So as I said, for a positive charge, the field lines emerge outwards from the charge, and for a negative charge, the field lines enter inwards towards the negative charge. So these field lines are emerging outwards from the charge Q1. So this statement is true. That is a positive charge. Q1 is a positive charge. Third statement, the size of Q1 is larger than the size of Q2. Well, you can tell the size of a charge, whether it's a lot of coulombs or not many coulombs, from the number of field lines either going in or out. So if there's more field lines emerging or returning to the charge, that would be a large charge. If there's less field lines emerging from the charge or returning to the charge, that's a smaller charge. If we count the field lines here, Q1 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 field lines emerging from it. Q2 has 1, 2, 3, 4, 5, 6 field lines returning to it. So Q1 has more field lines coming out, Q2 has less field lines going in. Q1 is a larger charge, has a larger magnitude. That's true. Final statement. The electrical field at point P is 0. So that's the electrical field at this point here. Well, that point is midway between the two charges, but both charges at that location are creating fields that act towards that are directed towards the right. The field from the positive charge, which comes radially outwards, will be towards the right. The field from the negative charge, which goes radially inwards, will be towards the right. And so both fields at that point are towards the right, and they'll superimpose to make a larger field. We can see that there's a field towards the right in this region if we just look at this bisecting line. Everywhere on that bisecting line, we see field lines that are traversing from the left and right, traveling from the left and right, indicating that there's a field that has a direction from the left to the right. So the field is not 0 at point P, midway between the charges. Okay, second concept question. In the second concept question, we've got a arrangement which involves a positive charge plus Q that's located at the center of a spherical conducting neutral overall cavity. That's shown here in this hatched region here. This is a cross section through that spherical shell with a cavity or a hole in the center. And we're asked a series of questions about the cavity, about the spherical shell. And so let's walk through those questions. So the first question says an amount of charge minus Q, negative charge, is distributed over the inner surface of the cavity. So a key thing about our cavity, our conducting cavity in equilibrium, is that inside the body of that cavity, inside the body of that spherical shell, inside the material, the metal material itself, the electrical field is zero. So I've denoted that. That means that the field lines that are emerging from the positive charge that's located in the cavity, at the center of the cavity, must be terminated by negative charges on the inner wall of the cavity to stop the field getting inside the conducting material itself. So actually there's a charge minus Q that's equal and opposite the charge plus Q that's distributed over the inner surface here of the conducting spherical shell on the wall that is facing the cavity. So that first statement is true. The second statement says that there's also an amount of charge minus Q on the outer surface of the cavity, on the outer surface of the spherical shell. So that's this surface here. Now we know that there's minus Q on this surface here, the inner wall, but we also know, we were told in the question, that overall that spherical shell was neutral, had zero net charge. So if we put minus Q on the inner surface, there must be plus Q distributed over the outer surface to make the spherical shell overall electrically neutral. So there's plus Q on the outer surface, not minus Q on the outer surface. This statement is false. Third statement says that the electrical field inside the conducting cavity is zero. Well, that statement is true. That statement was the basis, I wrote it down here, for which we analyzed the cavity, that the electrical field inside the cavity in equilibrium is zero. And so that statement is true. And then finally, we're told that if we ground the cavity, that is, attach the conducting spherical shell to ground with a wire, then the conducting spherical shell becomes positively charged. Let's imagine doing that. Here's a wire, and I've attached it to ground. What will happen if I do that? Well, look at the outer surface. The wire's attached to this outer surface, and the positive charges on the outer surface are repelling one another. Those positive charges will repel one another, and they'll leak off into the ground. That way they can get further apart. That will leave behind the negative charge on the inner wall of the spherical shell, the conducting spherical shell. And so this statement is false. The grounded conducting shell will become negatively charged, not positively charged. Okay, next concept question. In this concept question, we're asked to consider an arrangement of two capacitors, C1, C2, that are arranged in parallel, and they're connected to a 9-volt battery. And then we're told that the two capacitors have capacitances that are different from one another. So one is bigger, one is smaller. We don't know which one is bigger, which one is smaller yet. We're then asked a series of questions again, true-false questions, true-false statements, and then we go to respond whether they are indeed true or they are indeed false. So the first one is that the potential difference across C1 and C2 are different. This statement is false. Look, the left-hand terminals of C1 and C2, the two capacitors, are attached to the positive terminal of the battery. The right-hand terminals of C1, C2 are directly attached to the negative terminal of the battery. So there's the same battery terminal voltage difference between the plates of both C1 and C2. So their potentials are not different. Second statement is the charges stored on C1 and C2 are different. Well, an equation we might want to start thinking about was our master equation for our capacitance. Our definition of capacitance is the charge divided by the voltage. Now, in this particular case, we know that the two capacitances are different. We also know that the two voltages across the capacitance are the same. So the only way that the two capacitances are different, if the two voltages are the same, if the two charges on the two capacitors are correspondingly different. So the charges that are stored on the capacitors are different. This statement is true. Second statement. Third statement. The energy stored by C1 and C2 are different. Well, we met various equations for the energy stored by a capacitor. So the energy stored by a capacitor, I could write it as electrical potential energy. We could, for example, write as Q squared over 2C. Or we could write it as 1/2 CV squared. Both of these equations, one in terms of the charge, one in terms of the voltage, tell us the potential energy. Now, one of them is more useful, and one of them is less useful for addressing this statement here. The one I would use is over here involving the voltage, which we know is the same across both capacitors. I wouldn't use the one here, which is involving the charge, which is different across the two capacitors. Look at the one on the right involving the voltage rather than the one on the left involving the charge. We know the capacitances are different. We know the voltages are the same. So it must be that if the capacitances are different, the voltages are the same, the potential energies are different. So this is also true. Last statement, the equivalent capacitance of C1 and C2 is larger than C1. Well, this statement is also true. If you remember, when you've got capacitors in parallel, you build a equivalent capacitor that has more capacity to store charge. The equivalent capacitance is some of the individual capacitances. So the equivalent capacitance of the arrangement here will be larger than the individual capacitances of the two capacitors. Okay, I'm moving on to the first fully worked out problem, and it's one that involves two charges, and we're told their locations, and we're asked to explore the electrical field that's created by those two charges at a third location. That's the origin. And so let's work through this this problem. There's two parts to it, A and B. The first part of the problem says determine the magnitude and direction of the electrical field E1 and E2 that's created by the charges Q1, Q2 at the coordinate origin. So we're thinking about this point here. I will call it our field point. It's where we're interested in the field. And we've got to write down the size of the field due to Q1 and the size of the field due to Q2, and state the direction of the fields due to Q1 and Q2 to answer this problem. This is a problem that is involving what I would call Coulomb's law for the electrical field. We might call it the 1/r² law for the electrical field. The size of the electrical field due to Q1, now I'm just thinking about size right now, is given by the Coulomb constant times the size of Q1 divided by the square of the distance you are from Q1. And likewise for Q2, the size of the field, again, I'm thinking about the size right now. I'll answer the directions later. is the Coulomb constant times the size of Q2 divided by the square of the distance from Q2. I'm calling these distances R1 and R2. Well, to answer numerically what the size is, all we need to do is fill in the various quantities, the Coulomb constant, the charges, and the distances. And we know all these quantities. We can look up the Coulomb constant. We're told the values of the charges in this particular problem. And we know the distances from this sketch here and from the coordinates upstairs here. So let's just go ahead and fill in the numbers. 9 times 10 to the 9 Newton meters squared Coulomb squared. That's the Coulomb constant. The magnitude of charge number 1 is 5 microcoulombs, 5 times 10 to the minus 6 coulombs. And the distance that we are, the field point, is from this charge is 3 meters. It's this vertical distance, so it's 2 meters. It's this horizontal distance here. So we just got to fill in the 2 meters and square that. And I've already gone ahead and calculated the result. I got 1.1 times 10 to the 4. And the units of field are newtons per coulomb, because if we multiply by charge, we'll get a force, so it'll be newtons. Let's do the same thing for the second field. The strength of the second field, again, 9 times 10 to the 9 Newton meters squared per Coulomb squared is the Coulomb constant. We've got to multiply it by the charge. This time the charge for the second charge is 9 times 10 to the minus 6 coulombs. And we got to divide by the square of the distance. This time the distance from this second charge, Q2, on the vertical axis, that is 3 meters. And so I've got to divide by 3 meters squared. And if I calculate this, I've already done it, I got a value that is 9 times 10 to the 3 Newton per coulomb. And again, let me stress, I'm calculating the size of these two fields. I'm plugging in the sizes of the charges. So I just plugged in 5 microcoulombs, 9 microcoulombs. I didn't plug in minus 9 microcoulombs as an example. So those are the sizes. Now, what about the directions? Well, the directions of the fields we can just get from our knowledge that field lines emerge radially outwards from a positive charge. Field lines enter radially inwards towards a negative charge. So if we use that idea, Q1 is a positive charge. So its field at the field point will be away from the positive charge. It will be over here towards the left. And then the direction of the field due to the negative charge that's located upstairs here, that will be towards the negative charge. So that field will be directed vertically upwards. And I'll indicate that here. I could have written to the left, that would be perfectly fine in answer to this question. Could have written upwards, that'd be perfectly fine in answer to this question. I just drew pictures of the electrical field vectors instead. Okay, next part of the problem is to find the resulting electrical field. This is a problem of adding together these two field vectors. If I wanted to picture the addition, I've got one field that is E1 that's directed towards the left. Here it is. I've got a second field E2 that is directed upwards. Here it is. And my job is to find this resulting field here. I'll just call that E. And I'm going to specify that field by its magnitude. That's the length of this arrow here. I'll also specify by the direction. Say the direction with respect to the positive x-axis. So that would be that angle here. That's one way of specifying the direction. So the way to add two vectors, add two electrical fields, is by breaking the individual vectors down into their components, x and y components, horizontal vertical components, adding up their x and y components to get a total resulting x and y components, and then finding the magnitude and direction of the final electrical field. So let's go ahead and do that. So let's start with E1x, that's the horizontal component of the electrical field E1, and then there'll be E1y, that's the vertical component of that field. This is easy. This is easy because we've already got the size of E1, and we know it's all directed in the negative x direction. So this is minus 1.1 times 10 to the 4 newtons per coulomb, and its vertical component is just 0. So that was pretty easy. The hardest thing is reading my handwriting. The second electrical field, E2, we want its x component, E2x. We want its y component, E2y. And this too is easy. This field is just simply vertically upwards. There is no horizontal component. So E2x is 0 in this case, and E2y is 9 times 10 to the 3 newtons per coulomb. So that's writing out the two individual fields in terms of x and y components. Now we can add those fields together in this language of x and y components. So the resulting field, x component, I call it EX, is the sum of the two x components. That's E1x plus E2x. The resulting field's y component is the sum of the two y components. So that's E1y plus E2y. So I've got to add these components together. So for EX, I'm adding together this minus 1.1 times 10 to the 4 newtons per coulomb, and this 0 newtons per coulomb. So I'm just going to get minus 1.1 times 10 to the minus 4 newtons per coulomb, 10 to the plus 4, sorry. And then for EY, I've got to add together these two y components. It's 0 plus 9 times 10 to the 9 times 10 to the 3. And so if I add together those, I'm going to get plus 9 times 10 to the 3 newtons per coulomb. And so this is really the resulting electrical field in the language of x and y components. To complete the problem, what I'm going to do is actually find the magnitude. The magnitude of that field, which is the length of this vector E here, is by Pythagoras the square root of the sum of the squares of the vertical and horizontal sides here. So that's EX squared plus EY squared. I won't fill in all the numbers because you wouldn't read them anyway, but I did the calculation and I got 1.44 times 10 to the 4 newtons per coulomb. That's the size. And then finally, I want the angle. So to get the angle, I use a little bit of trigonometry. And I'm going to take the inverse tangent or arctangent of the ratio of the y component of the field to the x component of the field, so EY over EX. So this would be, EY is positive 9 times 10 to the 3. EX is negative 11 times 10 to the 3. So we're going to get a 9 over a minus 11. So it's a negative number that's a little bit smaller than 1. And if you calculate that on your calculator, you will get two numbers. Well, you'll get one number, but there are two directions that are opposite one another that have the same angle, have the same ratio of x and y components, but opposite angles, opposite directions. The two of them are minus 38.7 degrees. and the other one 180 degrees away is plus 141.2 degrees. So that's what I calculated. So the negative one would be a field in this direction. So this is a field that is measured opposite the counterclockwise direction of positive angle. So it would be a negative angle, and you can see it looks like it's about 38 degrees. Our solution is the opposite direction. It's the one that's 140 degrees roughly from the positive x-axis. It's this one here. So this is the correct one. And for our problem, this is just a mathematical one that has the same ratio of the two components, but is in the opposite direction. Okay, in this second fully worked out problem, we're asked to imagine a region of uniform electrical field. You can see it here in the sketch. It has equally spaced, same direction field lines. So that corresponds to a uniform electrical field. We're told its strength is 120 newtons per coulomb towards the right. And then in that field, we've got an electron, and that electron travels a certain distance in that field. It is 0.15 centimeters or 1.5 millimeters. So here's the electron's motion. Let me try again. Here's the electron's motion. And we're going to be asked several questions about the work done and about changes in energy as the electron moves from the right to the left under the influence of the electrical field, which is from the left to the right. There's an important point here. This electron is experiencing an electrical force because the electron is negatively charged. The force is opposite the direction of the electrical field. If it was positively charged, it'd be in the same direction as the electrical field. So here's the force. And it's that force that is acting on the electron. There's no other forces acting on the electron as it moves through the electrical field. And it's that force that does work, transfers energy to the electron. It's that force that is responsible ultimately for changes in electrical potential energy, changes in kinetic energy associated with the electron in the electrical field. So let's go through with that understanding and answer the question. So the first question is, determine the work done on the electron by this electrical force. Well, the work done by a force is the force, the strength of the force, the magnitude of the force. That's what I mean by just this F here, times the distance over which that force acts. I'll call that distance d. And again, that's just the length of the path. It's just a size, times the cosine of an angle, where that angle is the angle between the motion and between the direction of the force. So that's where the directions of the force and the displacement come in. This case, we're thinking about the force being the electrical force. So I'll put this subscript E on it to remind us of that. And we're thinking about the work done being the work done by the electrical force. And so we want to go ahead and find this, this work done by electrical force. And we're going to do it because we understand that this electrical force is due to this charge in this electrical field. The force itself is going to be the product of the charge, and the size of the force is going to be the product of the size of the charge times the size of the field. And so this equation here is put together our understanding of work done by forces and our understanding of the relationship between the electrical force and the electrical field. And again, I'm being clear here by putting the vertical lines around the charge that what I'm plugging in here is the size of the electron's charge. I'm accounting for the fact that it's negative in this angle here which accounts for the direction of the force and the direction of the displacement. Okay, all we've got to do is plug in the numbers now. So the size of the electron's charge, 1.6 times 10 to the minus 19 coulombs. The distance moved, that was 0.0015 meters. So it was 0.15 centimeters. And then the cosine, no, we need also the electrical field here. Nearly forgot that. That was 120, we were told this number, newtons per coulomb. And then finally, the cosine of the angle between the force and the displacement. Well, the force we said was towards the left, the displacement is towards the left, so they're both actually in the same direction. This is cosine of 0 degrees. If we plug all this in our calculator, I got a work done that was, this is going to be a positive number, and it's 2.9 times 10 to the minus 20 joules. So that was the work done by the electrical force acting on that electrical charge as it moves through the electrical field. The next two questions ask us, and I'll kind of answer them together, about the change in potential energy of the electron in the field and the changing kinetic energy as it moves through the electrical field. And we've got to be careful about both getting the sizes of these changes right and getting the signs of the changes right. What's happening here from the perspective of energies, when you do that work on the electron, it's positive work on the electron, that's going to increase the kinetic energy of the electron. So the kinetic energy is going to go up. The change in kinetic energy is a positive number. It's going to, that energy's got to come from somewhere. It's going to come from a decrease in the electrical potential energy. The change in electrical potential energy is going to be negative. So let's bear that in mind as we answer these questions. In general, the change in potential energy for a particular force is equal to the negative work done by that force. So in this case, it's the electrical force, the stored electrical energy, and it's the work done by the electrical force. And we know the work done by the electrical force. We've just got to plug it in here. And so that change in potential energy is going to be 2.9 times 10 to the minus 20 joules. And note, this is negative. This is negative because the potential energy of the electron went down. It decreased as the electron moved from right to left. Let's write down the changing kinetic energy of the electron. The changing kinetic energy of the electron due to the work done by a force is equal to the work done by the force, the positive work done by the force. In this case, is the work done by the electrical force. So if we just plug in that work done by the electrical force, it's going to be plus 2.9 times 10 to the minus 20 joules. So this is a positive number. The kinetic energy has grown. Positive work was done by that force, which means that it's adding energy, transferring energy to the electron. It's increasing the kinetic energy of the electron. So this is an increase in kinetic energy. The final part of the question says, determine the change in the total energy of the electron. The total energy of the electron, the change in the total energy of the electron, will be the sum of the various changes in energy of the electron. So there's a change in potential energy, and there's a change in kinetic energy. That's the only changes in this situation. And of course, one of them is positive and one of them is negative. They're equal in size. And so these two add up to 0. The net change in all forms of energy is 0. This is just energy conservation. Okay, now we have the final one of our fully worked out problems. And this problem involves a sort of simple electrical circuit in which we have a light bulb is connected to a 120 volt power supply, and that light bulb is dissipating energy. Light bulb is like a resistor dissipating energy. And we're told that the rate of dissipation of the energy is 40 watts. Maybe I would draw a circuit diagram for this. Here's my power supply. I'm picturing it as a battery, but it's a power supply. Here's my light bulb. I'm picturing it as a resistor, but it's a light bulb. And we're told that the voltage supplied by the battery or power supply is 120 volts. So I'll know that, denote that. And we're told that the power that's dissipated by the light bulb, that is 40 watts. And then we're going to answer several questions about this this simple sort of basic circuit. First question says, how much energy is dissipated by the light bulb in 8 hours? Really, this is a question about what power means, what power dissipated means, what energy dissipated means. What's the relation between energy and power? So power is the change in energy. So I could write that as, say, delta E divided by the elapsed time. It's the rate of transfer or change in energy. We want the energy dissipated, so that's the change in energy, the energy dissipated by the light bulb, over some period of time, 8 hours, and we can write an equation for that by rearranging this definition of power by just multiplying the left and right by the time interval. So the energy that's dissipated in the light bulb over 8 hours is the power that's being dissipated. That's the 40 watts or 40 joules per second times that length of time, which is 8 hours. I'm going to put it in seconds because I'm working in SI units, and that's 28,800 seconds. This is 3,600 seconds in an hour times 8. And that gives me a amount of energy, which is 1.1 times 10 to the 6 joules. And so that's my answer to the first part of the problem. Second part of the problem, how much charge flows through the light bulb in the 8 hours? So how much charge flows around this circuit in that 8-hour period? And the way I'm going to answer that is actually first figure out the current that's flowing around that circuit. That current is denoted by I, not Q. And I'm going to figure out that current that's flowing around that circuit in that 8-hour period. So let's go ahead and figure out the current first, and then we'll figure out the charge second. So to figure out the current, I'm going to use the relationship between current and voltage and power. I'm going to use this relationship because I know the voltage that's across the lamp, resistor. I know the power that's being dissipated by the lamp or resistor. The only thing I don't know is this current. So I can rearrange this for the current. That current is going to be the power divided by the voltage. And I know these two numbers. So it's 40 watts divided by 120 volts. So that's actually 1/3 or 0.33, and the units of currents are amps. So that's the current. And then if I want the charge that flowed during that period of time, I can use the definition of current. The definition of current is the amount of charge that flows. I'll call that delta Q. In some period of time, elapsed time, I'll call that delta T. If I want delta Q, the amount of charge that flowed, I can just rearrange this by multiplying through the elapsed time as I delta T. And then I can fill in the current is 0.33 amps. The length of time was again 8 hours, so it's 28,800 seconds. And if I multiply those together, I got 9,500 coulombs. So that's the charge that flowed. Finally, the last part of this problem. The last part of this problem says, what is the resistance of the light bulb? And we're told some information related to the light bulb. And we are told that the light bulb consists of a uniform tungsten length of 6 centimeters. And we're told that the okay, in the final part of this problem, we're asked actually two things. We're asked to find the resistance of the light bulb. We'll see that that's pretty straightforward. And then we're asked to find the diameter of the wire that glows inside the light bulb, under the assumption that that wire has a resistivity of 5.6 times 10 to the minus 8 meters. So that's a quantity that depends on the material that the light bulb is made from. It's made from tungsten. That's the resistivity of tungsten. And secondly, we're told the length of that wire that's glowing is 6 centimeters long. So based on those pieces of information, we're going to find the diameter of the wire. The first part, the resistance, is just an application of Ohm's law. Ohm's law tells us this famous relationship between current, voltage through a resistor and the resistance of the resistor. It's the law that says the current and the voltage are proportional to one another. In our case of our resistor, the light bulb, we know the current, we know the voltage now. We've worked out the current, we were told the voltage, so we can rearrange Ohm's law for the resistance. It will be the voltage divided by the current. And we can plug in the 120 volts. We can plug in the value for the current. It's 0.33 amps. And if we carry out that calculation, it's really just 3 times 120. It's 360 ohms. So that's the resistance of the resistor. The second part of the problem asks us to calculate the diameter of the wire. And to calculate the diameter of the wire, I'm going to use the relationship between the resistance of the lamp, which we know, and then those geometrical and physical properties of the lamp's wire. So the length of the wire, the cross-sectional area of the wire, the resistivity of the wire. And I'm going to solve for the cross-sectional area of the wire. So that's really the main bulk of the solution here. And I'm going to go ahead and do that. And then once we got the cross-sectional area of the wire, it's easy to calculate the diameter. So the key equation here is that one for resistance of a length of wire. And then this ratio of the wire's geometrical properties, its length and its cross-section. So if we look at this equation, we know the resistance, 360 ohms. We know the resistivity, we were told it. We know the length of the wire is 6 centimeters. Actually, the only thing here we don't know is the area, cross-sectional area of the wire. And so I can rearrange this equation for the area, multiply both sides by the area, divide through by the resistance, and I get the equation that the cross-sectional area is given by this expression here, resistivity times length, divided by resistance. I'm going to plug these things in. I've not got enough room now, so I'm not going to write them all out, but let me say what they are. Resistivity, 5.6 times 10 to the minus 8 ohms meters. Length of the wire, it's 0.06 meters, put it in meters. And resistance of the wire, that's 360 ohms. If you plug all those things in, you get the cross-sectional area of the wire, has units of square meters, is 9 times 10 to the minus 12 square meters. So it's a tiny, tiny cross-section. And filaments in lamps are very small cross-section wires, very, very narrow diameter wires, so that they glow hot, they glow bright. Well, now we know the area. Once you know the area, if you want the diameter, you can use the relationship between the diameter of a circle, circular cross-section, and the area of the circle. It's this relationship here, that the area is pi times the diameter squared divided by 4. This is probably more familiar as pi r squared. R is the radius. The diameter is twice the radius. So the radius is diameter over 2. The radius squared will be diameter squared over 2 squared, which is diameter squared over 4. Anyway, if you take this equation, we can rearrange this for the diameter. In terms of the known area, it will be 4a divided by pi. Again, I've run out of room, luckily, so I won't plug in all the numbers. We won't read them anyway. But if I take the square root of 4 times 9 times 10 to the minus 12 meters squared divided by pi, I'm going to get something with units of meters, because the square root of the meters squared will become a meters. And what I got was 3.4 times 10 to the minus 6 meters. And so this is 3.5 microns. It's a very, very thin wire. And lamps typically use very, very thin wires. That's why lamps, incandescent lamps, are gray. Those wires burn through, but they need to be very thin to burn bright, to be a light, a lamp.